All right, let's roll here. We're going to start section 9.2 today, which is graphing simple rational functions. You like titles? That's your title. There you go. Okay. So we're going to actually graph some stuff today. That's pretty exciting, right? We said we'd move along this year, meeting lots of different functions, and we're in a rational functions unit, but we haven't. That first section was kind of like, it is related, for sure, but this is, now we're getting to the meat of it. This is the stuff right here. We're going to get to actually show you a rational function, what it looks like today. And we're going to start with the very most basic rational function that anyone could ever give you, 1 over x. All right? Y equals 1 over x. Sounds simple, and you're like, I think I've seen that before. No, you haven't. You have not seen this. No. Don't. No calculators yet. Okay, we got to do this like pure mathematicians from the 16th century. Okay, here we go. Let's do this. We encounter this function the way we've encountered every other function in our lives. Yeah. What are you doing? That was so close. You can't spoil it. You can't spoil it. Don't spoil it.
How we found out the other day?
Don't spoil it. That'd be terrible. We're going to investigate this function the same way we've investigated every other function. We're going to plug in x and y today. What are you guys doing?
9.2.
Hi. We're going to plug in some points. So give me your favorite number, Marcelo.
47.
47. Okay. What do you get if you plug 47 into this function?
1 over 47.
1 over 47. Okay. Now, that's a little hard to plot, but it would be over here. Right there. Comma 47, comma 1 over 47. Like right there.
8 is my second favorite number.
You like 8 too? You think you get 2 numbers though? You think that's how special you are? Okay, fine. All right, 8 comma 1 over 8. 1, 2, 3, 4, 5, 6, 7, 8. Comma 1 over 8. So that's like somewhere down there, right? You agree? I mean, we've got to deal with partial boxes here. Is that okay with you? Just roll with it. Okay? What's your favorite number, Mitzi? 10. I know. That's a good one. What do you get? 1/10? So that's down here somewhere, even lower than the other one, right? Yeah? Jesse, what's your favorite number? 3. What do you get? 1/3? A little bit higher than our other numbers, so right about there maybe. 3 comma 1/3. What other numbers do you like?
1.
I like 1. Yeah. 1. What's 1 over 1? Oh, interesting. Greg, you want 1? 2, right? So 2, yeah, we could plug in 2, you get 1/2, right? But the point is, these keep getting smaller here. In fact, my favorite number is 100. What do you get if you plug in 100? 1 over 100. So tell me what's going on here. What is 1 over 100? That's a really big number. Oh, wait, no. It's really small. In fact, maybe let's be more precise. It's very close to what number?
0.
0. It's very, very, very close to 0. And if my favorite number was 1,000, then it'd be even closer to 0, right? It'd be 1 over 1,000. These things get closer and closer to 0. I think we have an idea that this behavior kind of gets closer and closer to the x-axis, right? And someone already uttered the word. What's the mathematical word for that? Yeah, it's an asymptote, right? We have this same kind of, this feels very familiar. We studied exponential functions recently, and log functions. We've thought about functions that do this. It has asymptotic behavior, getting closer and closer. Beautiful. Good job. What about, we're not done yet though.
-1.
Yeah, what if my favorite number is negative 47? What is y? If 1 over negative 47 or negative 1 over 47, same thing. Okay, so that's going to be over there. What about negative 8?
It's going to be the exact opposite.
Yeah, I feel like this is a little familiar, isn't it?
Well, it ends right there, and 1 and 1. What about -1?
Negative 8, comma negative 1/8. Negative 1, comma negative 1 will be on here, right? So what do you see? We're going to have kind of, we're going to have the same, is that enough to convince you that the behavior is basically the same over here?
If you plug in a negative.
Okay. Now, we've left still a mystery, so we're kind of filling out what this picture looks like. We've left a mystery region, though, close to the origin. So what would happen if we plugged in 1/2? Let's try that. Now we're getting crazy, okay? What happens if you plug in 1/2? What do you get for y? What is 1 over 1/2? Do you know the answer to that? What is 1 over 1/2? What is it?
That's 1 divided by 0.5.
Yeah, 1 divided by 2. 2. Right? How many halves are there in 1? 2, right? Or you could do the reciprocal, right? It's the 1 over something, it's the reciprocal. So yeah, it's 2. That should sound familiar as well. Okay, let's see. So 1/2 comma 2.
4 asymptotes in total.
So what do we get? What about 1 over 8? What do we get? What's 1 over 8?
8.
Yeah, it's 8, right? So if we're really close to the x-axis here, we're way up here at 8. Here.
Always gonna be the denominator.
Yeah, right? What if I did 1 over 100? What would I get? You get 100. So if I get really, 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 really close to the x-axis on the right, over here, then I'm getting really huge numbers. What if I were to get really close to the x-axis from the left?
You get it.
Like if I plugged in -1/2, what would I get? What would I get? The -2, right? So the same, I want to just convince you again that we get the same kind of behavior here as well. And last question, what if you plug in 0? What's 1 over 0?
Nothing. Alright.
I love the debate.
Nothing.
What is 1 over 0? If you don't know your calculator, that's right.
It doesn't say the y.
It says error, right? Because we don't divide by 0. It doesn't make sense, right? We could talk about y again, but I think you know that that's true, right? Right? Okay. So there is no value. We might even say that 0 is a number you can't plug into this function, right? We might say 0 is not in the domain of this function, right? We might say the domain of this function is everything except 0, right?
Oh, you write that. 0.
You just write x is not 0. X is not equal to 0. There are other ways to write it too, but that's cool. So we're dealing with a function that has a hole in its domain. That's cool. It's got 2 branches to it. You can see up here. Yeah, guys, we've just done it. We've just met our new friend, the reciprocal function. Check it out. Isn't he beautiful? On this card, I have it. We've met some of these other functions I have over here earlier this year. And now we're adding this to our list of friends, right? The reciprocal function would like to be your friend. Like, do you accept? Like, yes. Okay. Accept, man. Invite him into your inner circle. Okay. So cool, very simple graph, 1 over x, but you produce this really crazy picture with 2 branches. There's this nice symmetry to it. There's a lot going on. What else do we want to say? And yes, it has 2 asymptotes. It actually has 2 asymptotes. So don't you get this vertical asymptote behavior and a horizontal asymptote? Pretty cool. And it approaches on both sides of both asymptotes. So this is a good one to do after having studied exponential and log functions. Exponential functions always have a horizontal asymptote. Log functions always had a vertical asymptote. These kinds of functions have both. Get out. Isn't it so exciting? Okay. We should say before we go any further, because we're moving along here, right? We haven't yet actually told you what we mean by rational function. So let's stop and say what a rational function is. By a rational function, we mean a function that is the ratio of 2 polynomial functions. Okay? So we are probably not ever going to study ones that are quite this complicated, but just for the sake of example, I wanted to show you an example of what we mean. We mean any polynomial that you can think of, and by polynomial I mean polynomial, like we talked about in the first semester. Any polynomial divided by any other polynomial is a rational function of some kind. Now these get crazy. These rational functions get pretty crazy. This one probably has multiple asymptotes, right? You might actually have On a graph like this, you could have 7 asymptotes or something, right? On this one, it won't have that many, but you could have other like these things look crazy. Feel free to play around on your graph and start playing with these. We'll never do ones quite this complicated in this class, though. Okay. So we're going to start though with really simple rational functions, like like 1 over x. Okay. So that's the very simplest one I could think of is 1 and x for the top and bottom. Make sure you put the entire numerator in parentheses, though. Right? You don't have to. There's nothing special about this one. You can make up your own. I have no idea whether that's worth graphing or not. It's just I made it up for this slide. So, okay. And so rational. Why is rational a good word? Because, like I said, it's a ratio. Do you know what I mean by a ratio? Of one polynomial over another polynomial. That's ratio should make you. As soon as someone says ratio or rational, it should make you think fraction, right? So that is what this is basically. There is a 1-to-1 correspondence between these functions and the rational numbers. You see something crazy? When you graphed it? Yeah. Yeah, you can do some crazy stuff with these. Anyway, so I don't have much to say. This is not something that'll be tested on. I think it's worth saying, hey, we should stop and say what a rational function is. Okay? Because we were using the words. Okay. So we already graphed the simplest one. Y equals 1 over x, and I'm going to show it to you again. If you didn't get it already, then here's your second chance. Copy this down. Make sure you have this picture, because this graph is where we're going to start here. This is the fundamental building block of what we're going to be moving forward with. Y equals 1 over x. And so there it is again, a little prettier than what we did ourselves. And the shape that we get is called a hyperbola. New word for you. You know, like y equals x squared, we often call that a quadratic function of some kind. We call a parabola, right? We have like this other name for the shape. Well, this is a rational function. This is also called a hyperbola, though. I don't know if you remember from geometry. Did you do anything with conic sections? You may have heard of hyperbola. Is my point before. In fact, they do come up a lot in the world around you in ways you've never even thought of before. It's the shape that a Pringle takes on. That curve that a Pringle has. There are 2 curves to a Pringle. And they're called, the technical math name for a Pringle is a hyperbolic paraboloid. Did you know that? It's the technical math name for that shape. Well, I don't think the hyperbolic paraboloid would have fit on the can, so they shortened it. Yeah. But I think that was like a second runner-up, yes. Where else do you see him? I grew up next to 3 Mile Island. Do you know where that is? It's in Pennsylvania. I grew up in Pennsylvania, right on the Susquehanna River. 3 Mile Island is a nuclear power facility, and it has 3 cooling towers, one of which is no longer operational because of the meltdown in 1979. But and the 3 cooling towers have this shape. Have you ever seen? Even if you've never seen, right? They have this shape. The sides of those are hyperbolas.
Wait, is it just that one side?
Both sides. These 2 sides, here and here, that's a hyperbola. Those 2 things together. Oh, like if you were to look at this blue graph like this, that's what you're seeing. Okay.
So that together is hyperbola.
And it doesn't just look like one. It is one. Okay.
It doesn't look like a Pringle though.
Well, yeah, I know. Just one of them. Yeah. A Pringle has 2 curves to it though, like this and like this, right? And if you look at it from one side, it's curved this way. If you turn it 90 degrees, it's curved the other way, right?
Yeah.
Right.
You need Pringles to test it out.
Just test out the theory. I know.
You can go buy some this weekend.
What's up, you? Excuse me, I have to go take a selfie. Okay, I'll be right back.
Notes, write them down. Well, I mean, anybody can get it, sure. Oh, okay.
Take your notes.
I told them already, they don't listen to me. Write this down. He said he had things to do.
Who's chasing Lawrence, honestly? He's his own self-esteem.
You guys writing this down?
Check out our YouTube channel.
MIT. What'd you say? MIT and Brown and Yale. Wow, that's amazing. Okay. Wow. Okay. Good job, you guys. All right. Where were we? Hyperbolas.
Writing these down.
Right? So we already said it, but here we're saying it again. Two asymptotes. Vertical and horizontal with equations x and y equals 0. Bye, guys. And those change, obviously, right? You know that in a minute we're going to start moving these around, left and right, up and down, right? Because that's what we do. Isn't that how we do things? We always show you stuff and then we move it around, right? That's how we roll. So then these things will change. The horizontal asymptote will change, won't it? If you move it up and down, right? The vertical asymptote will change. It won't be x equals 0 if you move it left and right. Yes? So those will be up for debate if we move the graph. But on the basic one, the one we started with, those are the equations. It has two parts, which I've already called branches today, right? It has two parts called branches, and they've got a lot of symmetry that you can enjoy, right? When you get a point on one branch, you get another one on the other branch, right? There's this nice symmetry to it. Wonderful. Are you loving it? Oh, I thought of another place in nature while you're slaving away copying these and stuff. I thought of another place in nature that we think we see parabolas, or one that I could generate. What did I do with my superpen? Hyperbolas.
Hello, please pardon the interruption. Have Nathan Gonzalez?
Yeah? What's up? What do you need him for, Miss Spencer?
Well, he needs to sign out. So if you could send him to attendance to sign out, that'd be great.
Okay, well, we send him down.
Thank you so much.
You're so special, you get to go. Okay, all right. There, take that with you. You're probably next. All right. Yeah. All right. Yeah. So I was thinking about another place we see hyperbolas. We could generate hyperbola. Can you imagine if I had a cylinder, right? An empty cylinder. Can you imagine? It's empty. And I were to put a light bulb. If I were to put a light bulb in the middle, can you imagine? And I were to stand like a foot away from the wall. Turn all the lights off, but turn that light bulb inside of my little cylinder on. And then light would come out the top and bottom of my cylinder. Would you agree? And on the wall beside me, it would be all dark, except there'd be like this big like kind of curved pattern of light. It's the thing you would see on the wall in your living room if you were at night, all the lights were off, and you had like a lamp on in the corner. You'd see like this like curve of light on the wall. That, and there would be in fact two curves of light, wouldn't there? One coming out of the top of my cylinder, and one coming out of the bottom of my cylinder, and those would be forming the graph of a hyperbola, top and bottom curve of a hyperbola. So this kind of stuff happens lots of places in nature. And how would we move it around? Could we move it around? Like I said, x equals 0, y equals 0 are the asymptotes, unless we move it left and right, up and down. And how do we do that? Well, of course we do it in the same way that we do with every other function, right? A, h, and k, none of those should be a surprise. Remind me, please, what does k do? I know it's a constant, but what does k do? If you
equation.
take any function and add a number to the end of it, any function,
Moves up and down.
right click. It moves what?
Up and down.
Thank you, Marcelo.
Great, Kim.
Yeah.
Serious?
Oh,
No, you already said yes. You already said what.
I did already commit. I know. What does H do?
Left to right.
Ag moves it
Left to right, left to right. First.
What does A do? I'll give candy for A. Stretches it which way?
Wider or thicker?
What else does A do, Jesse? What else could A do?
Oh, almost dropped.
Shrink it. What else?
Expand.
Well,
The
you have
answer
to
is
distribute that
left to
10
right.
plus the 3 of us.
I know. I don't know if I can do it.
was I not right?
We all.
I mean, it does. Flip it. Yeah. But so A is all those things. So anyway, the point is all the things you know and love, right? K moves it up and down. H moves it left and right. A is a vertical stretch or shrink. Also, A can flip the graph. Instead of looking like this, it would look like this, right? You flip over the x-axis. And then if you've moved it left or right, that is, if you've made this is instead of x, it's x minus 5 or something, then the new vertical asymptote is however far you moved it, right? Likewise, if you moved it up or down, the horizontal asymptote is no longer y equals 0. It's y equals whatever you moved it to, right? This should not be a surprise. Sorry. I got excited. So my strategy when we go to graph these will be to plot both asymptotes first before anything else. And then find at least 2 points on one side and 2 points on the other side of the vertical asymptote. So these asymptotes, though, are going to be very, very critical. Right, so I've kind of given you some recipes for creating nice graphs of various curves. Right? So my recipe for this would be graph the asymptotes, both of them, find those first. Do them both, dashed lines, label them, please. Right? And then find 2 points to the left and 2 points to the right of the vertical asymptote to graph. And then if you want more, you can, but that'll give you a really nice picture. So the asymptotes are like not just like a little extra feature. They're like critical. It's the very first thing I would graph if I were going to graph these. It kind of forms the structure of the whole graph. 2 asymptotes. Pretty exciting that these have 2 asymptotes.
But there was 4.
Well, I mean, I know what you're saying, but there's only one asymptote. But you're right, it approaches it from both sides, right?
Oh,
and then there's only one vertical asymptote, but it approaches it from both sides. So that's what I just said. But here it is again in writing if you like it, okay? Plot and label both asymptotes. And by label, I always mean, please, like keep hitting you for points on your quizzes and tests on this. With the equation is what I mean by label. I always see people draw an asymptote and then they point to it. Asymptote.
That's what I did.
Is that you?
Yeah.
All right. Or they say equals 5 or something. No, I want you to write. Because now you understand why I've been such a bully about that, right? Because now it really matters. Do you understand that that's x equals 5? Or maybe it should be y equals 5 if we're talking about the horizontal asymptote, what the equation is? Okay. So we'll have to be careful about that. We'll do that as we go into some more examples. Plot the asymptotes, plot 2 or more points on either side, and then draw 2 branches, nice arrows, everything smooth, right? That's my recipe for success when you're graphing a rational function. And that is, I'm afraid, where we're going to have to stop. We're not even going to graph even one rational function today besides 1 over x. So sad. All right? But I said stop, but we're not done completely. I have this project I want to give you. Okay?
Project?
I know.
Do you forget that we have 6 other classes?
Don't worry, I'm thinking about you. I'm actually being really nice to you tonight. There is no homework tonight. Okay? Check it out. Okay, so I have these 9.1 packets. I'm actually not going to give those to you, though, until Monday, okay?
Nice. Very conservative.
Well, then you can take one right now.